The paleoclimate record teaches us that rapid climate change is incredibly hard on societies. The climate changes at the end of the Ice Age contributed to megafauna extinctions and forced major shifts in human subsistence. Droughts during the Holocene toppled civilizations, and those were natural variations, changes that societies had no control over. We're causing changes that are faster and potentially larger than those natural variations. With over 8 billion people to feed and house, many in areas vulnerable to climate change, the implications are staggering. Coastal cities face flooding from sea level rise. Agricultural regions face shifting rainfall patterns and more extreme weather. Water resources are stressed by changing precipitation and glacial melt. Tropical regions could see temperatures exceeding human survivability thresholds for outdoor work during heat waves. And of course, island nations could literally disappear. The humanitarian implications are enormous, and they are unequally distributed. Those who contributed least to causing climate change are often the most vulnerable to its effects. But understanding the problem is the first step toward addressing it. We know more about climate now than ever before. We can see changes happening in real time with satellites and monitoring systems. We can model future scenarios with increasing accuracy, and we have technologies available that could dramatically reduce emissions if deployed at scale. Solar and wind are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. Energy storage is improving. Carbon capture is being developed, though it's not yet proven at the necessary scale. The challenge isn't really technological anymore. It's political, economic, and social. Getting 8 billion people to coordinate on emission reductions, equitably distributing costs and benefits, and navigating competing interests. That's the hard part. Climate change is, in many ways, the ultimate tragedy of the commons. Individual actors benefit from burning fossil fuels, but everyone suffers the consequences. Solving it requires collective action at a scale humanity has never achieved. I know some people feel despair. The problem seems too big, changes too slow, obstacles too numerous. I understand that feeling. But humans have navigated existential challenges before. We survived the Ice Age through adaptation and innovation. We transitioned from hunting megafauna to agriculture, fundamentally transforming our relationship with the planet. We've overcome diseases, expanded lifespans, and created technologies that would seem like magic to our ancestors. We're not helpless. We're just facing a problem requiring unprecedented coordination. The 100,000-year cycle will eventually resume, assuming we don't permanently alter it. The orbital mechanics haven't changed. Naturally, Earth would eventually slide back into glacial conditions tens of thousands of years from now. But we're writing a new chapter, one where human activity is a major climate driver, not just a responder. We're affecting the planet on a scale comparable to the astronomical forces that controlled climate for millions of years. No species has ever had this much influence. It's both inspiring and terrifying. I often think about future geologists studying sediments millions of years from now. They'll see a clear marker, isotope ratios reflecting massive carbon combustion, extinction signatures, novel materials like plastics and concrete in the sediment. They'll recognize that something unprecedented happened during this brief moment. whether they'll also see evidence that we successfully navigated the crisis. That's still an open question. The answer depends on what we do in the coming decades. The cycle reminds us that climate is dynamic, sensitive to forcing, and full of feedbacks and tipping points. It's not a stable, unchanging background. It's an active system responding to inputs. For millions of years, those inputs were natural. Now we're adding a new input, and the system is responding. We're living through a moment unlike any other in Earth's 4.5 billion years. For the first time, a single species, us, understands the global climate system even as we're altering it. The knowledge and the power we wield are unprecedented. What we choose to do with them now will determine Earth's path for thousands, even millions of years. The Ice Age cycles have demonstrated how resilient life can be. Earth has endured dramatic climate shifts, and life has always found a way to survive, adapt, and even thrive. It survived the asteroid that wiped out the dinosaurs. It survived the ice ages, and it will survive this. But the real question isn't about survival. It's about whether human civilization, as we know it, will thrive. Or will we face massive disruptions that could have been avoided if we'd had the foresight to act sooner? I started by discussing the mystery of the 100,000-year cycle and the patient scientific work that eventually solved it. That same community is now warning us about anthropogenic climate change, using the very same methods that revealed the Ice Age cycles to us. If we trust the science that explained the past, then shouldn't we also trust its predictions about the future? It's becoming increasingly clear that we're pushing the system hard, and we will see significant responses. The window for avoiding the worst outcomes is closing. The Ice Age taught our ancestors to be adaptable and innovative. It's in our DNA. We can use those traits to navigate the challenge we've created, but we need to act collectively and quickly. The climate system has momentum and time lags, so actions taken today won't show their full effects for decades. But inaction today commits us to changes that will unfold for centuries. Every year of delay makes the eventual response harder and more disruptive. So, where does that leave us? We are 11,700 years into an interglacial period that should eventually end. We are armed with an understanding of how climate works, and we are actively changing it faster than natural processes typically do. The 100,000-year cycle that shaped human evolution is being overridden by human activity. We've become a geological force. The only question is whether we use that power wisely or recklessly. The answer will determine what kind of planet future generations inherit, and whether they'll view us as ancestors who rose to the challenge or as a cautionary tale of a species that understood the problem but failed to act. The clock is ticking. The cycle that sustained life for millions of years is still operating in the background. But for the first time, it might not matter, because for the first time, one of the species it created has the power to override it. And what we do with that power in the next few decades will determine not just our future, but the future of countless other species who share this planet with us. The Ice Age is over. The question now is, what comes next? And unlike our ancestors, who just had to survive the cycle, we have the power to shape it. That's both an incredible responsibility and an incredible opportunity. It's time to see what we do with it. It might sound crazy, but it's true. We are living in an ice age right now. I know it's hard to believe when the sun is shining, but this ice age actually began about 2.6 million years ago. And here's the really wild part. Every 100,000 years, like clockwork, our planet undergoes a massive transformation. Ice sheets advance, then retreat, over and over again. So, what does this cycle actually create? When Earth tips into a full glacial period, the planet becomes home to some of the most bizarre and magnificent creatures that have ever existed. I'm talking woolly mammoths trudging through frozen grasslands, giant ground sloths digging tunnels the size of your house, and saber-toothed cats hunting prey that weighed several tons. This 100,000-year cycle literally shaped the evolution of life on Earth for millions of years. About 10,000 years ago, most of these incredible animals just vanished. The cycle shifted, ice melted, and suddenly the megafauna that had dominated the planet for hundreds of thousands of years couldn't make it. We're still trying to figure out exactly why. Climate change, humans, or both? The debate is still raging. In this video, I want to break down this 100,000-year cycle, how it works, why it happens, what kind of world it creates during the cold phases, and what happens when it shifts back to warm. You're going to meet the creatures that thrived in Ice Age conditions, learn how humans survived and adapted, and understand why it all came crashing down so recently. And at the end, we'll talk about where we are in the cycle right now and what that means for our future. Let's start with the basics. An ice age isn't just a cold period. It's an extended chunk of time, millions of years, where Earth's temperature drops enough that massive ice sheets and glaciers take over large portions of the planet's surface. As I said, we're currently in the Pleistocene Ice Age, which kicked off about 2.6 million years ago and technically hasn't ended yet. Now, within any ice age, you get fluctuations. There are glacial periods where it's really frozen and interglacial periods where it warms up. We're in an interglacial period right now and have been for about 11,700 years. So when people say the Ice Age, they usually mean the last glacial period, which lasted from about 115,000 years ago to 11,700 years ago. That's when the ice sheets were at their biggest and the megafauna were running the show. During that last glacial period, the temperature was only about 6 degrees Celsius colder than today on average. 6 degrees doesn't sound like much, right? But we're not talking about 6 degrees in one spot. We're talking about 6 degrees worth of thermal energy being sucked out of the entire planet, all the oceans, all the land masses, the whole atmosphere. That's enough to completely transform the world. Huge ice sheets covered most of Canada and northern Europe. The Laurentide ice sheet in North America and the Fennoscandian ice sheet in Europe were kilometers thick in some places because so much water was locked up in ice. Sea levels dropped by over 100 meters. You could walk from England to France. You could stroll from Asia to Alaska across what's now the Bering Strait. The coastlines were completely different, and the landscape mostly tundra and cold grasslands, dry and windswept, nothing like the forests we see today. So what caused this? Why does Earth go through these dramatic swings every 100,000 years? The answer starts with this Serbian scientist named Milutin Milankovitch. Back in the early 1900s, he figured out something nobody else had really considered. What if ice ages weren't caused by anything happening on Earth, but by changes in Earth's position relative to the Sun? See, Earth's orbit isn't perfectly circular. It's slightly elliptical, and the shape of that ellipse changes over time because of gravitational pulls from other planets, mainly Jupiter and Saturn. Sometimes our orbit is more circular, sometimes it's more stretched out. And this cycle of changing from circular to elliptical and back takes about 100,000 years. That's the first Milankovitch cycle, called eccentricity. When Earth's orbit is highly elliptical, the distance between Earth and the Sun varies more dramatically throughout the year. This affects how much solar radiation hits different parts of the planet at different times. And here's the crucial part. It's not about how much total sunlight Earth gets. It's about where and when that sunlight hits. Northern Hemisphere summers are the key because that's where most of the land is. If Northern Hemisphere summers are cool enough that winter snow doesn't fully melt, the snow sticks around. Year after year, it piles up. Eventually, you've got ice sheets forming. And once ice sheets start growing, they reflect more sunlight back into space, which cools things down even more, which allows more ice to form. It's a runaway feedback loop. But eccentricity isn't the only cycle. There's also obliquity, which is the tilt of Earth's axis. The more tilted Earth is, the more extreme the seasons. This tilt varies on a roughly 41,000-year cycle. When Earth is less tilted, the difference between summer and winter is milder, which means summer might not be warm enough to melt all the winter ice. Ice accumulates, Ice Age begins. The third cycle is precession, or wobble. Earth wobbles on its axis the Earth, I've learned, is like a spinning top that's starting to slow down. And as it slows, that wobble changes which hemisphere tilted toward the Sun during different parts of its orbit. This happens, remarkably, on a 26,000-year cycle. I find it fascinating how this affects the contrast between seasons. Right now, the Northern Hemisphere experiences winter when the Earth is closest to the Sun, leading to milder winters than we might otherwise expect. But this flips during other parts of that cycle, resulting in much colder winters. When you combine all three of these cycles, eccentricity, obliquity, and precession, they work together to control Earth's long-term climate. What's truly strange, though, is that the 100,000-year eccentricity cycle is actually the weakest of the three in terms of how much it changes incoming solar radiation. The other two cycles should matter more. Yet, when scientists began drilling cores out of ocean sediments and ice sheets to reconstruct past climates, they found that the dominant pattern was this 100,000-year cycle. The weak cycle somehow dominates the whole system.